This meeting is being recorded.
For problem 12 from chapter 14, we're asked to take a look at these spectra shown here. So we have 6 spectra to examine and determine or match rather each of these compounds shown below, and then identify the significant signals that we've used to make our decision. So we're going to take a look at how we can interpret these spectra shown below. So let's take a look at A here. And we can begin by drawing our line around 1500 here. So we can draw a line up. And again, this is our fingerprint region, so we'll call the FP region here. So most of our useful information will be above that region. So after we draw that, we look for any signals in the 1600 to 1850 range. So that would be for double bonds. So 1650 to 1800. So CC double bonds. And then we can also look for triple bonds between the 2100 up to 2300. Right, these are both reciprocal centimeters. And this will be for those triple bonds. And then we can look specifically here, we see a weak signal right here around between 1600 and 1700. This would be consistent with an alkene. Right, so in that region here. And we also see a signal at approximately 3100 here. So together, this being a SP, sp2 rather, hybridized carbon bonded to a hydrogen in this region here around 3100. So we would use both of these signals to determine that this structure here would be what's represented in this spectra. Let's take a look at spectrum B. So once again, we'll draw that line around 1500, and we'll look to the left for any signals. So again, we'll look in the 16 to 1850 range for double bonds, the 2100 to 2300 range for triple bonds. And what we see here is a strong signal between 17 and 1800. So this signal right here, this is indicative of a CO double bond, a carbonyl, and only 2 of our structures. So we can choose between these 2 here, which would have that. And the spectrum does not match this compound here because there's no broad signal in the OH region here. So there's no OH stretch. So we would assume that this compound here would be the compound responsible for spectrum B. So again, we're looking for signals or lack of signals at times. So let's take a look at the spectrum for C here. So we draw our 1500 line once again, and we look to the left. So what do we see here? There are no characteristic signals in these regions or this region, either for any of these functional groups that we're familiar with. So we would expect this to be an alkene. And the only one of our options that's an alkene is that first structure shown. So we would expect for this one here to look like this. So this would be our structure, our alkene for, our alkane rather, no double bond, so an alkane will be our compound C. Next we have compound D or spectra D shown. And what do we have? We have a broad signal between 32 and 3600. So we know that we have an OH stretch, an alcohol. There are only this OH stretch present and nothing else over here. So we expect this to be the other alcohol that we didn't indicate before. So this structure here would be responsible for our signal in D, or our signals in D. Next, we see spectrum E here, and we see this very broad signal, extremely broad. So this is between about 2200 all the way up to 3600. This is a characteristic OH stretch for carboxylic acid. And what we see here is also the CO, the carbonyl stretch of a carboxylic acid around 1700. So both of these would contribute to us determining this compound could be a carboxylic acid, and the only one shown in our groups up top here is this structure here. So this is actually a dicarboxylic acid, but this would be our structure E. Again, for those two stretches that we see, the OH stretch between 22 to 3600, and then our carbonyl CO stretch at 1700. In our last spectrum now, we see two signals around here. So we have one at around 3450, and then the other one around 3350. So if you recall, this could be due to the symmetric and asymmetric stretching of an NH bond. And a primary amine would give us right, this type of stretch. So we have an amine that's bonded to one R group. So the only structure that would be capable of producing F spectrum would be this right here.